Welcome to the ninth lecture on undergraduate analysis, Math 4310 at CU Denver. This corresponds to material from Chapter 5 in the Kenneth Ross book. And this is by no means, again, comprehensive on this material. In fact, my main objective in this lecture is to actually show you how to use the existence of derivatives to write functions in a form that are convenient for proving other results. That's kind of one of those takeaways that students really struggle with. Like, what are they supposed to get out of knowing the existence of a derivative? How is that useful for showing something else? So I just showed the definition of what it means for a function to be differentiable at x equals a, and it's in terms of a limit of a ratio. You might be familiar with this from undergraduate calculus. I hope that you're familiar with it from undergraduate calculus. We take the limit as x approaches a of f of x minus f of a over x minus a. In calculus, you might have seen this in terms of like a limit as h goes to 0 of f of x plus h minus f of, well, I guess I would actually have a here, a plus h minus f of a over h. And you can actually just show that this is completely equivalent to this other form by doing a change of variables where you let h equal x minus a. But that doesn't really matter. So we're not going to dwell on this. I'm going to assume that you're fairly familiar with at least taking derivatives of functions. Now, if this happens, I mean, this form is convenient, as we'll see. We call the limit the derivative of f at a, and we use this f prime of a notation that hopefully is also very familiar. Now, here's the first thing that I'm going to show. It's just using the idea of a function being differentiable to rewrite it in another form for certain values of x. So what we take away from this is f prime of a is really equal to this limit as x goes to a of f of x minus f of a over x minus a. So let's go through this following process and see how I can write a function in a different form. If I take f of x, what I can do is I can, at a point a where it's differentiable, I can add 0, right? This is just adding 0 to the equation. I say it's f of x minus f of a plus f of a. I haven't changed the function at all. Now, what I could do is I could multiply a certain part of the function by 1, right? If you add 0, you don't change anything. And if you multiply 1, you don't change anything. So I choose to multiply by 1. This is just a multiplication by 1 if x is not equal to a. So now this equality only holds if x is not equal to a. If x is equal to a, it's not defined because then I have a 0 over 0. But if I don't, then what I did was I grouped f of x and f of a together, and I multiplied by x minus a over x minus a. And then I just regrouped the two. So again, I still assume that x is not equal to a, but now I took the numerator, x minus a, that's a factor out in front, and then I have the divided by x minus a, but that's now dividing into f of x minus f of a, which it was multiplying to in the previous step. So what does this just mean? Well, the limit as x approaches a of everything exists in this form, right? The limit as x goes to a of x minus a is just a minus a is equal to 0 by our standard limit results that we see from functions when you study this, earlier in the material when you're going through the material carefully. Then the limit as x goes to a of f of x minus f of a over x minus a, well, that's what we call the derivative. That's f prime of a. And the limit as x goes to a of f of a is just f of a because it's a constant. A is fixed. So by standard limit theorems, which are just kind of like our sequence theorems, if all these limits exist, then sums and products of limits also exist as the sums and products of the limits. So the limit as x goes to a of f of x, if we define this function f of x except at x equals a in this way, can be written as the limit as x goes to a of x minus a times f of x minus f of a over x minus a and f of a. Right, all the stuff we just did. And all those limits exist, so we can basically take the limit of each component separately, and we get 0 times f prime of a. So f prime of a is a real number, right? We're saying this limit exists and is finite, so it's some real number. So f prime of a exists as a real number here. So 0 times it is well defined at 0. And we show that the limit as x goes to a of f of x is equal to f of a. And that's one of the characterizations of continuity that you would get from back in like chapter 3 in the Ross book. So that proves this theorem. If f is differentiable at a point A, then f's continuous at the point, something we remember from calculus. But we got at it in an interesting way, or at least maybe it doesn't seem so interesting, but it is interesting to me at least. The takeaway message is that we often use knowledge of the derivative or in its existence to rewrite a function or create a function that has some form convenient for proving a desired result. In this case, we have that, hey, functions are continuous if the limit as x goes to a of f of x is equal to f of a. That implies continuity at the point a. How can I use the existence of a derivative to prove that that's true? And it goes through this process of, well, what do I need to do? I need to somehow get f of x minus f of a over x minus a showing up. And you say, well, if I need to get f of x minus f of a, if I'm going to subtract f of a, I need to add f of a so that I add 0. That was the first thing we did. Then we know we need to shoehorn in this x minus a in the denominator. You can't change things. So you have to multiply by 1. You multiply by x minus a over x minus a. Rearrange terms, look at the existence of all the limits, and apply standard results. And that's the main message here. That's how we use the derivative to kind of rewrite the function in a different form for all values of x not equal to a, and then we send to the limit. All right, let's look at kind of another example where we use existence of limits to define a function that has a convenient form for proving a result. Well, or at least we'll get to one. So theorem 5 here is if f is defined on an open interval containing x naught, f assumes its maximum or minimum value at x naught, and f is differential at this point, then its derivative is equal to 0. This is one of those things that we call a critical point from back in calculus. This above strategy, or excuse me, this above result justifies this common strategy that we have of differentiating functions to find all the critical points and locate the maximums meant to do optimization problems using calculus. So that is also useful in proving this following result. So this is just going to present kind of a sequence of results to get where we want to go, which is Rolle's theorem. If f is a continuous function on the closed interval a to b and it's differentiable on the open interval a to b, and f of a is equal to f of b, then there exists at least one point where the derivative is equal to 0. So the main idea is if it's differentiable and the endpoints are exactly the same, and I say I have a continuously differentiable function, there has to be some point, like its max or its min, that occurred in the middle by theorem 5, and its derivative had to be 0 there by things that remember from calculus. All right, now, once you have those two results, Rolle's theorem gives us a nice tool for proving the mean value theorem. Specifically, if we could take any continuous function f on a, b, and define the linear function as the line that goes through the point a, f of a, and b, f of b, then you define the function. So you use this idea that the function is differentiable, and you get this new function g here equals f minus L. And now what you've done is you made g of a equal to 0 equal g of b. And I'll show this in pictures to give you the main idea. And what this means is I can now apply Rolle's theorem to g and then make the conclusion I want on f. Okay, so the mean value theorem is that there's basically some point such that the derivative is equal to the average change in value, right? There's some point where the tangent line is parallel to the secant line. You might remember that from calculus. Here's the basic idea in pictures. Here's my function, a graph of my function f of x from a to b. And the idea is f of a and f of b are maybe different. And this means that Rolle's theorem does not apply here, right? I don't know that there's some point where the derivative of f is equal to 0, and that's not even what I'm trying to show. But what I can do is define this function L as just the equation for the line that passes through the 2 points a f of a and b f of b. That's what the graph of L is showing. Then if I graph what g is, it's f minus L. What I'm basically doing is now getting a function where Rolle's theorem applies to it. And then what does that mean? That means that there's some point where g prime is equal to 0. Well, g prime is equal to f prime minus L prime by properties of derivatives that you would prove if you were going through this material very carefully. Well, f prime minus L prime being 0 means that f prime is equal to L prime at this x value. Well, what's L prime? L prime, you're talking about the slope of a line, right? The derivative of a function at a point tells you the slope of a tangent line in there. Well, a line, every tangent line is just the line for a function that's a line. And the line that passes through these 2 points is given by, take the slope of the line that goes through those 2 points, f of b minus f of a over b minus a, rise over run. So that's kind of it. We use the existence of the derivative that f was differentiable. We rewrite a function in a more convenient form to apply another result, and then we get the desired result we want on the function f, right? Which was now that there is some point x where f prime of x is in fact equal to the average rate of change, the slope of the secant line through the interval AB. Okay, so the mean value theorem says if f is continuously differentiable with a bounded derivative, then it's also Lipschitz continuous. So I provide a proof of that here, but that's just an additional result. I don't think that's in the book, but I just thought it was useful if you wanted to see it. So I'll let you go through that on your own time. I'll just stop with the this main idea and the main takeaway of derivatives, or one of the main takeaways at least, is that we often use the existence of derivatives and the idea that a function is differentiable to write other functions in more convenient forms for where other results can apply. Like in this case, that Rolle's theorem applies to G, and what we did originally was that we could use the idea that if the limit as x goes to a of f of x is equal to f of a, this implies that f was continuous at a, and we do that if we have differentiability of the function f. We prove continuity at the point by going through this process that I went through earlier to rewrite the function in this other form, right? And I know that's kind of a mess. I'll clean up this document before it's posted for you. So one of the main takeaways, but something to not shy away from, is think about how can I use the existence of the derivative of a function at a point or on an interval to write another function so that other theorems and results apply to it. So that's something I think students often struggle with. So here's just a couple of examples of theorems and results that we use that technique. So that's it, and I'll talk to you next on integration.